All right, so as I mentioned, we've now gone through more or less our internet this week's material. Will go on the fundamental theory of calculus, which is essentially more integration, or rather more about how to do integration in certain slightly trickier cases. So now we're talking about the definite integrals. So we're having some constant a, and our function is actually an integral from a to x of some function. And on this integral, then the fx has an antiderivative of capital F. Oh, better look that direction. So if we differentiate this integral, it should return back to fx. How? Well, the lower bound there, the lower limit of the integration interval is a constant. If we differentiate a constant, the derivative is 0, and the upper limit of the integration returns fx. So that way, the differential of this kind of integral will end up being just fx. So we can see this from, if we have integral from a to b fx, we will have some function b minus some function g. So those are the same function which are some antiderivative of f, doesn't matter which, because that plus c will cancel out, and b is the upper limit and g is the lower limit. So now this is done several ways. When I'm running by hand, I'm using a different notation typically. So the formal one is that if we have capital F as the antiderivative of the non-capital F, lowercase f, then integral a to b fx is this capital Fx, and then we use this notation that tells we still need to calculate the integration limits, which are upper limit minus lower limit. And well, here just demonstrated, okay, if we put plus c's there and minus c on the part where we then subtract the lower limits, then the c's will cancel out. And by hand, I personally like this notation where after integrating, we have this slash notification from a to b, but it's really hard to use on Microsoft Excel because it thinks that's a division sign on the formula editor. Okay, so now this is how we use this information is mostly now by examples. And let's do some. So first one, from 0 to a, x squared. Well, first check what's the antiderivative of the function. So go to back to elementary functions and then check their antiderivatives. Well, that's already an elementary function of x to the power of something, which has the antiderivative of increase the power by 1 and divide by the new power. So we get x cubed over 3, and then substitute a and 0 for x. And now if you insist on having some antiderivative, now when we can select any antiderivative, we could select the one that has plus c equals 0. So the c would be 0. And well, a cubed minus 3 minus 0 cubed, a cubed over 3 minus 0 cubed over 3, well, is a cubed over 3 minus 0, which is just a cubed over 3. Then if we have two limits, so it doesn't really matter if it's some yet unknown constant, or if we know the constant, we can use the maths the same way, of course. If we have lots of unknown constants, then we cannot really as nicely reduce the function value to some nice numerical value. Well, same thing. What we first do is find the elementary parts and find their antiderivatives. So we have the x squared, which is the same. Then we have minus 3 times x. So we have minus 3 times half x squared, which I've already combined here to 3 over, whoops. Yeah, it just doesn't let me paint the text now. So 3 over 2 x cubed. And then the antiderivative of 2, which is 2x. And substitute 2 and 1. So 2 cubed over 3 minus 3 times 2 squared over 2 plus 2 times 2 is 4. And then minus, and it's good to use, in this case, use a parenthesis to make sure you don't confuse yourself, because we're now getting minus minuses. So minus 1 cubed is still minus 1 over 3. So we get minus 1/3. And then we had minus 3 second parts, and minus 1 cubed is 1. So it's still minus 3 over 2. And 2 times minus 1 is minus 2. Okay, collect terms. So I've just collected by the denominators of the quotients to make it easier to calculate. We get 9 over 3, which is 3, minus 9 over 2 plus 6. Okay, 3 plus 6 is 9. Full part of this fraction is minus 4, and then we still have minus 2 left. 9 minus 4 is 5, minus half is 4.5. Or 4.5 if you prefer the decimal approximation. Well, that's actually an accurate one. 10 typical questions are: what is the area between our function and some other function? Relatively common, the other function is an axis. So we're still thinking about the 2D case, so we're not going to the function rotates around the axis things, but that comes later. Okay, well, we could use the formula for solving a second-degree equation, but now that c equals 0, well, we can just take x as a common factor. We can see immediately that this is 0 if x is 0, or 3 minus x is 0, and 3 minus x is 0 when x is 3. And substitute those as limits of integration. Integrate as before, substitute values, and now we get what is the original function. So 3 times 3 squared is same as 3 cubed. So that's why we get both of the numerators as 3 cubed over 2 and minus over 3. The lower part goes to 0. So we get 27 second parts over 3 over 2, because one of the powers of 3 and divided by 3 cancel out. So we get 13.5 minus 9, which is again 4.5. You may prefer to do the maths different ways. So one way would have been that I would have stated everything, because there's a with the smallest common fraction. So then we would have a nice regular calculation on the numerator, and then just slap the smallest common denominator there. The answer will be the same. Okay, area delimited by sine, and now, okay, on the average, sine is 0. If we consider the x-axis, so define the limits. So this is just the first hump of the sine. If I can run MATLAB, I could show this. So from 0 to pi, but this is just regular. We have the limits. So and what becomes sin? Well, sine is well, the derivative of sine is cosine. The derivative of cosine is minus sine. So the antiderivative of sine is minus cosine. Substitute from 0 to pi, so we get minus cosine pi minus cosine 0. Cosine pi is minus 1, so we get minus 1, which is 1. And cosine 0 is also 1, so we get minus 1, which is also 1. And 1 plus 1 is 2. So always nice to draw these if you can. So a function of t, sin t, and let's see what this draws. Okay, so now the limits aren't quite right. The most useful command in MATLAB is help, because this probably tells me which way to put the limits. So x min, x max as a 0 and pi, and those are in those brackets because it's actually a list of limits. Now this is just one of these, and apparently area under the curve is 2. Right. Okay, then the different thing, we have y equals 1, a constant function, and then some function of y. So now we need to find the intersection of these functions. So previously the axis is essentially function of y equals 0. That's the definition of the x-axis. We could have also two functions. So how do we do this? Well, the generic way is that we find out the intersections of the functions and then integrate both with the same limits and figure out which one is greater, and just subtract the smaller area from the greater one. Of course, need to check that if functions pass the axis, then we know that we in integration get this negative area, so need to be careful with those. So a simple case, or then we could combine those functions, and now when we know when they intersect, then have a new composite function with, well, not a composite function, but a combined function which has one function minus the other function. So we need to solve when 1 equals 5 over x squared plus 1. We'll clearly see that this is the same case when the ratio of 5 to x squared plus 1 is 1. So multiply by x squared plus 1, which is, by the way, always positive, never goes to 0. So that's a nice property to have for quotients, or at least a denominator side. So x squared plus 1 equals 5. And minus 1 both sides, x squared equals 4, x is plus minus 2. And now we could either integrate 5 x squared plus 1 minus 1, which is the larger function subtracted by the smaller one. Or then we could divide the integral as plus or minus, so we can integrate separately to 5 over x squared plus 1 and 1, which is what I've done here. So the area, now I've taken the constant out, so we get closer to the elementary function. So 5 times this integral of 1 over x squared plus 1 minus the integral of 1. Well, the integral of 1 is just the area of a rectangle, which is 4 units wide, 1 unit high, so it's minus 4. Remember to carry the minus sign here. And now this 1 over x squared plus 1 has an interesting property because it is actually symmetrical. I have MATLAB somewhere here open still. So if we f-plot, well, x if you insist, x squared. Now I need to use these dots because otherwise this goes funny with the vectors MATLAB uses. So it actually calculates in parallel all the values within the range it calculates. So we get something like this, the symmetrical function. So instead of going from -2 to 2, we can state that the area is twice from 0 to 2. So with the even functions, you can do that as we had last lecture. So I'm gonna swap these out. And now just times 2, here was 5, so it's just times 10. Since the integral, we already integrated this 4 here, and there was a minus sign, so it's minus 4. And the integral of this is the arcus tangent. So we get arcus tangent 2 minus arcus tangent 0. Arcus tangent 0 is 0, so what we get is 10 times from here, arcus tangent 2 minus 4, which is roughly 7.07. But in most cases, this accurate answer is already okay without the decimal approximation. So I really like the decimal approximations because if you have this formatted in a different way, it's a really quick way to check if it was roughly on the same ballpark. Okay, this looks hairy, but not too bad. So if we integrate these are relatively elementary stuff. So e to the power of minus x, well, e to the ax is ax also on the integral side. Well, 1 over a, but there's minus 1, so we get the same result in this case, plus the antiderivative of cosine is sine. So that's our integral. And now apply the limits. The upper limit here is 0. So I had the habit of applying the upper limit first when I'm calculating these. E to the power of minus 0 is 1. And minus in front of that, minus 1. Sine 0 is 0. There's a plus sign. So that's just 0. And well, anyway. And then we get minus pi over 2, e to the minus e to the power of minus pi over 2 is just minus e over pi over 2 plus sine to the power of sine of minus pi over 2 is minus 1. So we just get e to the power of minus pi over 2 sorry, minus e to the power of pi over 2. This is really easy to get confused here. Minus 1. And this is what we reduce from, or subtract from minus 1. So minus 1 minus minuses. So we just get e to the power of pi over 2. And we wanted to have the mean. So that's the integral of this, and the mean is by definition divided by the interval length. Interval length is pi over 2. We divide that by pi over 2. So we multiply that with 2 over pi, and we get that, which is decimal approximation, so it's just more than 3. And if you do this with CAS, at least some computer algebra systems notice that hey, there's we do have these trigonometric functions and e over x, so maybe it tries a hyperbolic expansion here. But that's good enough already. Improper integrals. What's the value of that? Anyone want to have a try? And now, in this case, we need to notice one little thing, that the integral has still the area interpretation. So what does that look like? That if we f plot 1 over x, technically it has the integral of a natural logarithm of the absolute value of x, which would suggest that the integral with those limits would be 0 if we just apply the formula. But the function looks like this. So it goes to minus infinity and plus infinity. Let's put the grid on to look slightly nicer. So, okay, common sense would suggest that, okay, these areas are the same size, but both of these areas have the size of infinity. So we get, if we divide it at 0, we would get infinity minus infinity, which is not defined by regular mathematics. So actually, this relatively simple integral is unsolvable. As of now, at least. So need to check also what the function we're integrating looks like. So if there are discontinuities, then even if the integrated form would have this disappeared, then we still cannot calculate the value of the integral because the function does not have a value at some point, have a real value. So the infinity is not part of the set of real numbers. Okay, now we had, in the very beginning of the lecture, we had this statement that we have, if we integrate this kind of if we differentiate this kind of integral statement, we get essentially the upper limit if the lower limit is constant. So for the first one, essentially now if the lower limit contains the variable, then we just swap the limits and put the minus sign. That was in last lecture, one of the basic integration rules for definite integrals. And now we just integrate that. Well, we don't need to really integrate it. Those cancel out each other, and we get minus e to the power of minus x squared. Or we could no, we can put the square term. So also make a difference between in parent if power is in parentheses minus x squared or minus x squared. Those are different things. Then the next one. Now we have a function there as a limit, and we also have the x squared in before the integral statement. So we need to apply the product rule to differentiate this. So we are finding the derivative of g. So x squared and just this integral, and so derivative of x squared, just integral, is the first part. We're applying the product rule, and then x squared and the differential of the integral. Okay, and then when we differentiate something like this, then this 5x here is our internal function. So we need to apply the chain rule. So this is what happens over here and over here. So we get the integral of this, and it has the internal function input here, and 10 times the derivative of the limits. So the derivative of 5x is 5. And I left this undifferentiated here, but we could then still calculate the non-integrated here. So we calculate the integral of this, but it's relatively easy to do, and collect the terms. Not necessary, but makes it easier to read. So there's a few big ideas here. So this was product rule application, and then on the right side part, we applied the chain rule. Okay, now we have two functions and two limits. And now remember, we can divide the function or the integral by some other constant, then flip around. So we have from 0 to x cubed and from x squared to 0, and then flip around the other one to get and then add a minus sign in front of that. Now we can do the both ones easily, and we get nice power train here. So in this case, we'll make it look a bit nicer by combining the constant powers. And yeah, we have had a function now on the integral limit, so needed to apply the chain rule as well. Okay, integral equations. Actually, if we go for real, then the full electric circuit connected in series modeling system is actually an integral equation and a differential equation. So in its full form, it is we had this RL circuit, which had a resistor and a coil. So it has this R times I plus L times the time derivative of I. And then if we add a capacitor, it would be 1 over C times the integral of I. So that's the full equation for electric circuits. So one way we could deal with that is just just differentiating both sides once. Works especially nice with those kind of DC circuits where the voltage disappears because constant voltage, so it just drops off. And with this example, now we differentiate once. The differential of f is f dash, and then we differentiate what's on the right side. Differential of 2, the derivative of 2 is 0, and then we get 3 times the derivative of this integral statement, which is fx, so with 3fx. Now we need to figure out what function has a derivative which is itself 3 times. Well, if a function has a derivative that is itself, it would be e to the power of x. And then if we apply what would be the kind of a chain rule part here, what's inside the EX to get the constant 3, well, that's 3x. So the fx is some multiple of e to the power of 3x. And now how to fix that, what the c is. Now we can make that integral statement disappear there. So we're integrating from 4 to x. So what if we calculate the value of this function with the value of x equals 4? Well, integral from 4 to 4 is always 0 by the area interpretation. The width of the area goes to 0, then the integral value goes to 0. So 3 times 0. So f4, with the function f with the value of 4, with the parameter 4 is 2. So c times e to the power 3 times 4, so c times e to the power 12 must be 2. And solving for c, we get c equals 2 to the power of e minus 12. So negative powers is on the divisor. Input that as c. So now c is 2 divided by e to the power of 12, but it's nicer to put in this form because now we remember we have two powers with the same base. We get 2 times e 3 to the power of 3x minus 12. Anyone need a break? No? Everyone's still awake? Good. Okay. This looks interesting. We're doing limits, but we're having limits of n going to infinity of a sum. This is essentially the definition of an integral. So we're having something that's infinitely narrow. So now if we remember that the definition of the derivative was that we're kind of calculating slopes, and as the area under the secant gets infinitely narrow, then that becomes the tangent. Now we're kind of if we reduce the integral to a sum, and then the individual sub-intervals that we sum over have the width of 0, then that becomes the integral. And we're having an infinite number of these to sum up. Oh, this is a really nice thing to think about 9 o'clock in the morning. So we're having infinite number of infinitely narrow, or actually well, yeah, infinitely narrow is not the correct term, but now I've actually myself forgot what the correct term for this differential was. Anyway, we go from 0 times we go from 0. So when we have this n equals infinity there, and j is 1, well, j anything else than infinity doesn't really matter here. It's 0 when we divide by infinity. We're going to n over n times pi over 2. The n's cancel out, so we go to pi over 2. And then anyway, by definition of integral, we can write this as an integral from 0 to pi over 2 of cos x, which is, well, the derivative of sine is cosine, so the antiderivative of cosine is sine. And sine from 0 to pi over 2 is, well, sine pi over 2 is 1, minus sine 0 is 0, so this is 1. So this is 1/2 of the hump. We actually knew this already because we earlier integrated this 1/2 of of a sine, and now we're integrating half of the hump of the cosine. Okay. At this point, it would be actually nice to maybe have a little break if anyone feels sleepy, because the next thing also is quite theoretical. My usual trick at this point, I've also been, people on the internet don't see it because I'm not in front of the camera, I've been sitting down. I would like everyone to stand up. Here's a little trick. Okay, point at me and give me a thumbs up. You know what happens next. Switch hands. Okay, everyone is almost woken up enough. These are kind of when you need to do different movements on different sides are really good for your brain. Also, things like rotate your arm and leg on the same direction and try to switch the other to do the other direction. So, okay, this is actually should be on the previous lecture before the intermediate part. So this is still part of the basic calculating of integrals. I actually should change it here, so you can combine elementary integrals or divide to elementary integrals. So the first one is just we can divide the integral at each point, and then we calculate the elementary integrals separately. And then in this case, what we have the lower example, I haven't had it expanded here, but then we would probably want to calculate what this x plus 1 to the power 3 is, and then divide this quotient at the pluses, so we then can cancel out most of the x of the divide by x's, and it becomes a lot easier to integrate after that instead of trying to use some other form of quotient rule here. And then the big topic here, so method of substitution. So essentially, I hope everyone remembers the chain rule. We already tried using it a few times on the examples. And this is the opposite of the chain rule. So if we have something in the integral that we can state in the same form as we know what was the end result of the chain rule. So we notice that we can divide here an external and internal function and detect that inside our integral is the derivative of the internal function. Then we can state the integral as a composite function plus c. And if you remember something from this from high school, those who have had the topic, then you probably remember that it was introduced that we calculate this du and what it is, and then du is something dx, and then x dx is something, so we can replace those, and we'll go through this by a few examples. Okay, the first example, we have we need to integrate x over x squared plus 1. Maybe we have two models and we need to have something that's a quotient of these two models, and we'd like to know what's the integral. Okay, so now we might try u is x squared plus 1, and its derivative would be 2x. So if this is essentially just implicit differentiation of this function as if it were u. So the derivative of u is u. Then we have 2 times the internal function here, which is x, and derivative of 1 is 0. And at dx, because we had this x. And if we solve here, x dx is du over 2. Okay, so we could replace x squared plus 1 with u, and then we have left over x dx, which we replace by du over 2. Well, actually, in this case, we didn't need to add anything, but in some cases, you may want to add a number and reciprocal to get one disappear, if it's easier to think that way. So we could just go on with du, and there would be an extra 2, which we can drop off. So this comes just du over u, which we can integrate. It's just natural logarithm of u. And we had this times half added up. So we get half the natural logarithm of u. Then substitute back what the u was. And we get half ln x squared plus 1 plus c. And now when we have, if we want to, this is okay, this is perfectly okay as an answer. But if you want to go further, we might remember that with logarithms, if we have something times logarithm, that's the same as something times the logarithm's internal part to the power of that something. So we could also state this as a natural logarithm of x to the power of 2 plus 1 to the power of 1/2, which is the natural logarithm of the square roots of x squared plus 1. Okay, more funny stuff. We're having a natural logarithm here as an internal function. So what if we replace that? Okay, do we have the other part? Yes, we do, because integrating a natural logarithm, well, derivative is of the part 1 over x, so we do have the derivative there as well. Now we still have a leftover extra 3, so then we'll add to 1 over 3. So this becomes just the integral of sine, which has the antiderivative cosine. So 1 over 3 cosine u, substitute back to 3 ln x, and we got our answer. Slightly harder ones. So then it's not always obvious from the first glance, but then, for example, the first example here, we can group up x squared plus 4x plus 4, which is x plus 2 squared, and we have left over 1. So now if u is x plus 2, we can get 1 over u squared plus 1, which is the antiderivative of arcus tangent. So we get arcus tangent u, and then put u is x plus 2. And the next one is slightly more complex, because now we're getting this in a bit nasty form. So now what we're going to do is we take e to the power of x squared 2x as a common term, which in so what happens here is that this ex is okay, but this minus 1 becomes e to the power of x 2x and e to the power of minus 2x. So essentially, when this doesn't go to 0 within the area where within domain function, then we're allowed to do this. So this is e2x divided by e2x, which is 1. Now we take the common term of e2x. So we have e2x times minus 1 minus e to the power of minus 2x. And now that we can take out of the square root by taking the square root of the common term, which is 10 e to the power of x. We move this upstairs, so reciprocal, add the minus to the power. And now we have e minus x here, we have e minus x here. Replace that one, and we have the derivative of r cosine. We get r cosine u, and now then substitute back into minus x. And there we go. Okay. Now, we have a different kind of problem. This clearly looks like it is using the chain rule, but there's no dash here. So we have just some function and the internal function and its derivative, but we don't really figure out this one. And now, well, we can just integrate that function. So that it goes that way too. And now, if we integrate that one, we need to swap the limits. Potentially. So when we do the swap, we need to consider the limits as well. I actually may have a typo here. I need to check my notes because this probably should have those capital A, capital B. So we need to consider 10. Well, there are two ways to deal with this. Yeah. So if we consider this kind of a thing, from 0 to 8, we have a hairy looking example, but and then this area bounded by. Okay, let's check the first one. Okay, so clearly, if we go to u equals something, we get, so now we're having definite integrals with the method of substitution. Previously, we had just this indefinite one. Okay, so we consider the u equals something, and then du, clear unit there. Okay, this dx over the square root of x plus 1 disappears, and we get 1 extra 1/2, which we can take out the integral. And we then get clear cosine u du. And there's method 1 is that we swap limits. So we calculate that, okay, what are these x values if we use u's? So substitute the limits to the statement of u. So if u is square root of x plus 1, then x equals 8 has square root of 8 plus 1, which is square root of 9, which is 3. So u equals 3. And same thing with 0, we get square root of 1, which is 1. Or then we can keep the limits as x equals 8, but then remember to write the x equals, not to get confused at which unit the limit was in. So the integral is choosing u, and then whichever way we do, so either we calculate the value directly while we're still using the u as a unit, or whether we need to substitute back to u equals x plus 1, and then we can use the original x limits, then we can calculate the value. So you don't need to substitute back to u equals x plus whatever the x function is. You can, if you have, calculate what the limits are in terms of u. But if you want to keep the original limits, which may be occasionally easier if the u statement is complex, or you would get something like fractional stuff or whatever, then you could then substitute back to what the statement of u is, and then use the original limits. Slightly more hairy, but we noticed that we have cosine, which is the derivative of sine. So we do have replacement here. This becomes just u squared. And the limits are nice because from 0 to pi. So now I just replaced them with some a and b. I didn't want to calculate those yet, so we can plug those limits in there. We get u is 2 and u is 3 as a limit. So from 2 to 3, this statement, we can calculate that and we get the answer. or we could then substitute back this sign case, but in this case it's easier to not substitute back. Also, both this integral of u squared has 1/3 over u third, so it might be in this case easier to just take 2/3 out as a constant and then calculate those powers. Okay, and that was a lot of stuff in a very short period of time. Anyone head hurts? Okay. We'll have something about this next week. I'm not sure if I want to add some trouble by having practical problems this time, so we might actually have this kind of a traditional schoolwork related to integration next week. This week we're still talking, in the exercise we're talking about the differentials. And if you're thinking about what exactly you need to do there, then one way would be that you can, so what I'm expecting to see as an answer, so one simple way to solve this week's exercise is showing that what the next statement of x is as some function of the previous one. So you should state what you need to calculate to get the next step. And after that, it's okay to just table the values. So step number and x number. This one, if needed. Technically, for the answer, you don't necessarily need to calculate the value of the last one. Maybe it is difference might be useful, and then just state the values here, and this shows that you've done the work. The answers, the numerical answers of the last part, so how many you needed of these and what the location was, if I remember right, are already marked on the exercise problem sheet. Help will be available. I will be today on the exercises, and on tomorrow's exercises we will have Dr. Makkuasa, because I'm having a meeting at the same time. I will be with you on demos, and so the big question is, do I have a ready demo on the previous ones? But probably we're going to do on the demos, we're going to do numerical integration. So how it's really done, so to speak. So when we're having typically unknown functions or signals, then we can still integrate them by letting the computer do it. All right. Anyone having questions on the internet? If not, then okay. Well, I didn't think we were this fast because we're using last year's schedule. We're halfway next week already. But doesn't matter. Then we have some more time to rehearse in the end of the period. All right, this is it. So we have a stop recording.